नहीं, अपन नॉर्मल लैपटॉप में कर लेना, सेम वैसे करना, कुछ नहीं करना है उसके अलावा आपको।
मतलब बस ये वाला करना है ना, डाउन वाला।
पेन ड्राइव लगाएंगे वो, ये तो देखो ये हो गया मिनिमाइज, ठीक है, ये डेस्कटॉप आ गया।
हाँ हाँ
पेन ड्राइव लगेंगी,
ठीक है।
हालांकि हम भी यहीं रहेंगे, वो नहीं है कोई इतना, तो पेन ड्राइव लगा लेंगे। उसके बाद में वो कंप्यूटर से आ ही जाएगा, पीपीटी ऑन करनी।
को करना है क्या, विंडो पी?
विंडो की आप भी यहीं हैं क्या?
नहीं, मैं तो पीछे
अच्छा।
भी करूँगी, पर थोड़ा सा ठीक है ना, तो ये मैम के साथ आ जाऊँ। विंडो पी ना?
हाँ, ये प्रोजेक्टर के लिए होता है विंडोज़ पे। इसमें ये होता है कि आपको दोनों तरफ दिखाना है तो डुप्लीकेट कर दो
अच्छा।
विंडोज़ पी करके।
और अगर सिर्फ स्क्रीन पे
सिर्फ
जाना है तो
सिर्फ
पीसी स्क्रीन
सिर्फ पीसी स्क्रीन पे जाना है तो आप ये करोगे ना, तो उस पर सिर्फ ये डेस्कटॉप आ जाएगा, देखो पूरा गायब हो गया। अब कुछ भी कर सकते हो आप यहाँ पे अपना काम,
कहाँ, नीचे
पीपीटी
वाला
से
तो आ रहा है?
ये तो रहेगा,
अच्छा, ये तो रहेगा।
ठीक है। बाकी हम यहीं रहेंगे, ये एक प्रॉब्लम क्रिएट होती है बड़े ऑडिटोरियम में। बाकी विंडोज़ पे करोगे, डुप्लीकेट करोगे तो दोनों पे चलेगा सेम एज इट इज़।
तो अपने को जो सरस्वती वंदना चलाई है तो अपने को
मैं चला दूंगा अंदर से, वो
अच्छा,
सब कैंसिल है ना,
अच्छा ठीक
मतलब
है।
On behalf of the management and the faculty and the entire family of JECRC University, it is my privilege to welcome each and everyone present here in the inaugural ceremony of the first International Conference on Innovations, Advances in Material Science and Sustainable Goals, IAMSSG 2025. It is indeed a matter of great honor to welcome the illuminaries of today's ceremony on the stage, and I request Professor Girdhar U. Kulkarni, former President JNCASR, Adjunct Professor CENS Bangalore, as our chief guest to please adorn the stage. I request Professor Takuyuki Ichikawa from Hiroshima University to please adorn the stage. He is our guest of honor. I request Professor Victor Gambhir, President JECRC University, and Shri S.L. Agarwal, Sir, Registrar JECRC University, and also Professor Vidhi Dubey, Dean School of Sciences, and Professor Pranav Saxena, Convener and Head of the Department, Physics Department, to please come upon the stage. विद्या ज्ञान प्रदायिनी ज्ञान प्रकाश भरो, मोह अज्ञान और तिमिर का जग से नाश करो. With these thoughts in mind, I invite the dignitaries for lighting the lamp of Ma Saraswati, without whose blessings no event of knowledge can reach success according to the Indian belief system. Thank you all. Coming now to the reason that we all are gathered here today. So once again, I extend a very warm welcome to all the distinguished guests, respected professors, researchers, and young scientists gathered here for the International Conference on Innovations and Advances in Material Science for Sustainable Goals, organized by the Department of Physics, JECRC University, Jaipur. Material science, the science that lies at the heart of every technological revolution, is what connects imagination with innovation. From the silicon chips in our devices to the perovskite cells powering the next generation of solar panels, from quantum dots that illuminate our screens to biocompatible materials that heal the human body, materials truly define the way we live, move, and evolve. Material science, the science of understanding and designing matter, is at the core of modern innovation. It shapes everything around us. From the tiniest chip to massive energy storage systems, every leap in technology, whether in clean energy, space exploration, healthcare, or computing, begins with a leap in materials. This international conference titled Innovations Advances in Material Science for Sustainable Goals emerges as a dynamic platform to explore these frontiers. This 3-day conference brings together brilliant minds, scientists, academicians, industry experts, and young innovators to share cutting-edge research, ideas, and possibilities that align with the Sustainable Development Goals. At its heart, IAMSSG 2025 is more than an academic event. It's a celebration of curiosity, creativity, and collaboration. It represents our collective commitment to science that not only advances knowledge but also serves humanity and the planet. I will now take the opportunity to felicitate our dignitaries on the stage, and I request Victor Gambhir Sir, President JECRC University, to please present a bouquet to welcome our chief guest, Professor Girdhar U. Kulkarni. I also request Sir to please present the tricolor garland representing our belief in our national product and our mark of respect, a shawl as well. Thank you so much, sir. Next, I request Shri S.L. Agarwal, sir, Registrar, JECRC University, to please felicitate our guest of honor, Professor Takayuki Ichikawa. Once again, I request sir to please present a bouquet. Our symbolic tricolor garland and our mark of respect, a shawl to sir. Thank you so much, sir. Thank you, sir. Moving ahead, I will now introduce our convener, Professor Pranav Saxena, sir. Dr. Pranav Saxena currently serves as the Professor and Head of Department of Physics at JECRC University, Jaipur, with more than 25 years of experience in higher education and research. He obtained his MPhil and PhD degree from the University of Rajasthan with specialization in high energy physics. His research interests encompass quantum field theory, Gauge-Boston phenomenology, and applied electromagnetic in communication. Dr. Saxena has authored several research articles in reputed journals and international conferences. Under his constant guidance, the Department of Physics at JECRC University actively promotes research, innovation, and community engagement. Dr. Saxena is deeply committed to empowering and strengthening the faculty by providing professional growth opportunities, connecting them with domain experts, and organizing national and international academic gatherings. I request sir to please deliver the welcome address and give us a brief of the conference.
Good morning, everyone. Sabhi ko namaskar. It is a matter of great pleasure and pride to welcome you all of you to the occasion of inaugural ceremony of Innovations, Advances in Material Science for Sustainable Goals. And this activity is actually supported in the association with 3 academic and research body: Indian Association of Physics Teacher, Rajasthan Chapter, Material Research Society of India, Rajasthan Chapter, and Soft Material Research Society. At the outset, I feel privileged to extend my warmest greeting to our chief guest, Professor Girdhar Kulkarni sir. Professor Kulkarni is an adjunct professor at the Center for Nano and Soft Matter Sciences, CNS Bangalore, and former president of Jawaharlal Nehru Center for Advanced Scientific Research. Professor Kulkarni has a long tenure at Jawaharlal Nehru Center for Advanced Scientific Research, starting his journey as a faculty of fellow in 1995 and serving till the position of presidentship up to August 2025. Professor Kulkarni is a distinguished scientist in the field of nanostructured materials, molecular electronics, and quantum devices. With his pioneering work, he has earned impressive credentials, including over 14,250 citations, with an H-index of 75, with an I-10 index of 256. This figures itself a big testament to his global impact and enduring influence on the field, sir. Sir has been recognized with a series of national and international awards and medals. With such luminous profiles, sir, we are obliged to having with you, sir, and giving your kind presence. Thank you very much, sir, for being with us in this occasion. I further also take this opportunity to warmly welcome our guest of honor, Professor Takayuki Ishikawa from Hiroshima University, Japan. Professor Ishikawa is globally renowned expert in hydrogen storage, material and sustainable energy technologies. Again, his research excellence is reflected with 10,500 citation with an H-index of 55 and I-10 index of 190, which speaks itself as global leadership in clean energy research. And I think this is a straightforward attention to the sustainability in the energy. So thank you, sir. Thank you very much for being with us at this occasion, sir. I further express my warm greeting to the distinguished speakers who is of the dais, Professor Sushmi from IIT Hyderabad, Professor Sujoy from Kalpakkam, Professor Ankur from Gyanvihar University, and many more are there. So I can't name each and every one. And other distinguished fellow who have joined with us online through this YouTube link, and across the country as well as across abroad, such as Professor Sharif from USA, Professor Moon Shu Ho from Taiwan, Professor Manish from Florida, Professor Ranveer from Illinois. So there are many distinguished speakers who have joined virtually this inaugural ceremony, and also the advisory board member which are being the part of this inaugural ceremony. I welcome to our President, Professor Victor Gambhir, sir, Dean Ma'am, Professor Vidhi Dubey, and the Registrar, sir, Professor S.L. Agrawal, sir, for being with us always in such activities and inspire to do and continues to flourish the physics or the science. Last but not least, the registered participants, including scholars, young faculty, students of PG, they have registered with us with a number of approx, I think 130 today we have reached it, and this number reflects that the conference is in right direction with true spirit and true energy. This conference is actually an attempt to contribute the vision which has been raised by our Honorable Prime Minister Narendra Modi, sir, the Viksit Bharat by 2047, and this is a small contribution in their agenda. And this conference is a platform where the science meets the sustainability. The objective of this conference is not only to share scientific advancement, but to bridge fundamental research, technologies, innovations, and sustainability goals. I think many of us are well aware and know that this year holds a special significance with the declaration of International Year of Quantum Science and Technology. I'm sure that many of us are well known, and the whole world is celebrating the 100th century year from the birth of modern quantum science. One of the major applications of quantum technology is quantum materials. from quantum dots and topological insulators to superconductors, 2D system, for example, spintronics, which are redefining the possibilities in energy storage, sensing, computation, communications, and sustainability. So I believe in the context of this International Year of Quantum Science and Quantum Technology, the theme of our conference is perfectly aligned, and I expect that how these frontiers can contribute to the sustainability and global progress. Therefore, in coming 3 days, over the next 3 days, the conference will feature a series of talks in the shape of keynote, plenary, and invited, which will be delivered by eminent speakers which from across the country, from top-notch institute, IITs, national laboratories like CSIR, NPL, IUAC, and from renowned university too. Beside this, there is a session that we have kept, research industry academy session, for an open discussion within the participants, scientists, and industrialists. And as usual, there is a separate or individual showcase for the poster session and oral presentation in the coming 3 days, which are sponsored by our Royal Society of Chemistry, American Chemical of Society, and Indian Association of Physics Teachers. So in totality, I believe by the end of this conference, we may come up with the positive outcomes as a takeaway, and most probably the main factor or main cause to conduct this or such kind of this activity is to strengthen or to generate or to initiate the new research collaborations, innovative ideas, which could be transformed into technology sustainability. And of course, there is a high quality publication after a peer reviewed in a selected journals, Scopus Index journals. Personally, I believe that there should be a strengthening of global research network dedicated to the vision of quantum and sustainable material. So therefore, I am going to wind up my words. So to all our delegates, I request, including especially a research scholar and young minds, to stay tuned in all the session, remain engaged, keep the session live by keeping interactions, more discussions, so that the outcome as I outlined may be fulfilled. At last, I would like to quote that material are not just physical matter that surround us, they are the medium through which imagination become innovations. So stay engaged, enjoy these 3 days in wonderful weather, and thank you so much for being with us. Thank you.
Thank you so much, sir, for setting the goals of the conference with such clarity. I'm really excited to introduce our next speaker, Victor Gambhir, sir, Vice Chancellor, JECRC University. Sir is the academic head of JECRC University and brings with him a distinguished record of leadership in higher education. He has previously served in reputed institutions such as SGT University, Maharshi Markandeshwar, deemed to be University, Manav Rachna Educational Institutions, YMCA Institute of Engineering and Technology, all at the highest positions in the organizations. With extensive experience in academics and institutional development, Sir's areas of expertise include quality assurance in higher education, accreditation, procurement, project management, and educational administration and management. He has been instrumental in various academic and development initiatives such as establishing new institutions, launching innovative courses, and developing progressive curricula. There is hardly any domain in academia where Sir does not hold deep insight and authority. A widely read and erudite scholar, he remains a constant source of inspiration and guidance for all of us at JECRC University. I request Sir to please deliver the inaugural address.
Very good morning, Namaskar. I extend very warm welcome to chief guest of this inaugural ceremony, Professor Giridhar Kulkarni, Adjunct Professor, Center for Nano and Soft Matter Sciences, CENS, Bengaluru. Our guest of honor, Professor Takayuki Ichikawa, Graduate School of Engineering and Technology, Hiroshima University, Japan. My colleagues on the dais and distinguished speakers. Specifically, I would like to name few: Professor Peter Mangwane from South Africa, Professor Archana Lakhani, DAE CSR Indore, Professor Sushmi Badhulika, IIT Hyderabad, Professor Sujay Chakravarti from DAE CSR Kalapakkam, Professor Ranveen Kumar, Dr. Hariom God University MP, Professor Naveen Kumar from Maharishi Dayanand University Rohtak, Professor Y.K. Vijay, who is a very well-known and a renowned face in the field of physics, and other distinguished guests who are here today, online, offline, with us for this first international conference, namely Innovations, Advances in Material Science for Sustainable Goals, organized by Department of Physics, School of Sciences, in collaboration with various bodies. I also extend very warm welcome to all the delegates who are presenting their papers and who will be involved in networking with some of the top-notch scientists and experts in the field of materials in general and physics, material in particular and physics in general. So it is a proud privilege to be here, to stand before you, to tell you about JECRC institutions. We started our journey in the year 2000 by establishing a private self-financing engineering college called Jaipur Engineering College and Research Center, which happens to be one of the most preferred private college even today in the state of Rajasthan. They offer about 8 undergraduate programs right now, and there is a student strength of 5,100 plus as on date. This university was established in the year 2012 with 3 schools and 511 students on rolls in the first year. Today, in the year 2025-26, we have more than 20,000 students enrolled in 25 undergraduate programs, 26 postgraduate programs, and 21 PhD doctoral program leading to PhD. The faculty strength is more than 500 on regular basis and about more than 125 visiting professors. We basically claim to be innovation-led research institutions. We have right now 423 research scholars enrolled with us, and 123 PhD degree have been awarded so far, and the number of alumni from these institutions stand at about 16,000 plus. When we talk about our research profile, we have published more than 1,600 research papers in Scopus and Web of Science Index journals, with the total citation of more than 20,000, H index of 65, and I-10 index of 425. And in last almost 13 years, we have organized about 16 national and international conferences, predominantly international conferences, where more than 4,000 research papers have been published in the Scopus and Web of Science Index journals. And this is the first attempt by Department of Physics. They have been holding other international level events. Recently, we held Aditya L1 mission related conference in our campus, which was organized by Department of Physics, and last year also one such conference was organized, but the conference where papers are being presented, that is being organized by Department of Physics for the first time, and I congratulate all the organizers who have taken very keen interest. I see that for last almost 6 to 8 weeks, everybody is engaged in organizing this event in a successful manner. Opportunities like this give us opportunity to know what is happening in the contemporary world on the themes which we have chosen for this particular conference. All the delegates who have come from across India, I am sure that they will take advantage of this opportunity to network with the scientists, with the keynote speakers, with the professors, and with each other. And this will kind of become a landmark for them to know what exactly has happened in the chosen theme. So once again, I extend very warm welcome to our chief guest, our guest of honor, all the esteemed guests, and I also extend a warm welcome to my own colleagues from JECRC University and other students who are present here. Thank you very much. Namaskar. Jai Hind.
Thank you so much, sir, for your good wishes and for the blessings. Unveiling of the abstract book. Ladies and gentlemen, we now move on to the most significant moment of this conference, the unveiling of the book of abstracts. This compendium is not just a collection of abstracts, it is a reflection of diverse scholarly voices, innovative ideas, and rigorous academic inquiry around the globe. The Book of Abstracts stands as a testament to the intellectual vibrancy of in this international gathering. It encapsulates the essence of the research contributions, highlighting the synergy between disciplines and the spirit of collaboration that defines academic excellence. Thank you so much, sirs and ma'am. It is indeed a moment of great honor and privilege for us to have Professor Girdhar U. Kulkarni amongst us as the chief guest for today's inaugural ceremony. Professor Kulkarni obtained his PhD from IISc Bangalore in 1992, followed by postdoctoral research at IISc and Cardiff University. He joined JNCASR in 1995 and is a professor of Materials Unit since 2008. He has served as chair of the Materials Unit, Dean Academic and Faculty Affairs, and was director of CENS from 2015 to 2020, where he now continues as an adjunct professor. He served as the president of JNCASR during 2020 to 2025. He has held visiting positions at institutions including Cardiff, Tokyo, Trieste, Pisa, and Paris Sud, and was an adjunct professor at Purdue University from 2009 to 2011. With over 340 publications, he has mentored 36 students. He is a fellow of all major Indian science and engineering academies, as well as of TWAS, RSC, and APM, and also a J.C. Bose Fellow. I request sir to please address all of us with his plenary talk on AI is not sustainable. What we need is ABI, that is Artificial Biological Intelligence. I request sir to please address all of us. Yes, sir.
खाना एप्पल का बनेगा
ये है ना?
क्या ओडी है ओडी
नहीं ऑडियो नहीं
अच्छा
वो तो जरूर
अच्छा लाइट अच्छा ड्राइंग ठीक है
बराबर
चेंजेस नहीं तो चेंजेस चाहिए तो
चेंज नहीं ज़रूरत नहीं Good morning. President Professor Victor Gambhir, Guest of Honor Professor Ichikawa, Sri Agarwal Registrar, Professor Dubey, Dean SOS, and Professor Saxena, Convener, eminent speakers from many places, distinguished colleagues, participants, students. I am so pleased to be part of this event, and particularly during the inaugural event, I consider that to be a great honor. I was very well received, very kind hospitality, wonderful, having a wonderful feeling. Thank you so much. I have 1 hour, but we lost some time. Probably I'll stick to 45-50 minutes and allow some questions. Probably just the end of my speech. Also maybe during tea, coffee, lunch or whatever. I'm here till afternoon. Am I clearly audible at the back? This talk is actually meant for the younger generation, so not for the front-seated people here. If I am not audible, I have to raise my voice or connect another mic. Raise your hand. Am I audible? Oh, thank you so much. Thank you. See, when I was young like you, no one spoke about sustainability. We were always talking about technologies, advancement in technology, engineering, whatnot. But today it has become a buzzword. Why? Because we have realized we cannot go on with what we have developed. So this emergence of sustainability is actually to make things going much more efficiently and also being friendly to Mother Earth, right? I mean, we have to rely on Mother Earth and we cannot move away that easily, at least. People talk about civilization on other planets and all, but it's nothing of conceivable in the near future. And I'm so glad that this university, JECRC University, has taken the initiative to conduct a conference where in the title itself we have sustainable goals. And in a way, sustainability and material science, they go hand in hand. Other than living like an animal in the natural world, we have to take things around us, convert them into materials. Having realized the exotic properties, we must exploit them to turn into some sort of technology. If you look at a rock, because of its property being very hard, it was sharpened and used as a tool in the past. I'm talking about our ancient past of mankind. Similarly, we have come off now through quantum evolution and all that, understanding at the atomic nuclear level, at bigger at cosmos level also, that how to make use of the available matter, having realized the properties, having fine-tuned the properties with composition, size, shape, everything gives rise to new type of property. Graphite, if I take, is one property, but if I can slice out an atomic layer from it, it becomes altogether different property, two-dimensional graphene. Similarly, if I take any metal, It can form a ring, a jewelry component, whatnot, or it can become an electrode in some electronics. The moment I convert that into a tiny, tiny nanoparticle, then it exhibits different properties. So having realized that the same set of materials under varied compositions while making composites or alloys, we have now smart alloys, shape memory alloys, so on and so forth. So you can realize how material properties can be tuned to our advantage and exploited for technology, right? But having done so, are we really keeping in mind sustainable goals? So I'm really truly touched by this particular title, and it has become my passion also in the recent past to actually keep studying how technologies can be made to become more sustainable. Having said so, and in my own research and also generally reading about sustainability, I have realized is nothing like a very focused, partial approach. Of course, it is focused, but it is a very holistic approach, I would say. When you think of sustainability, you not only worry about the track in which you are taking your research or your activity, you have to worry about everything else because it has implications on everything what you do, right? On the environment, on the health. So it is not that we have to depend on the certification agencies to tell us what you have done is not acceptable because it doesn't go well with the nature or environment and whatnot. We as students of nature, researchers, we have to worry about inculcate the same qualities in us as we begin at the 0th level. So we talk about TRL levels, right? 0, 1 to going up to 9 when the product reaches maturation. But sustainability has to be with us all the while. So I'm going to give a technical talk. This is not a general speech. And that is how we learn from nature, because nature has been around. It has been around because it has learned itself to be sustainable. What I mean nature is the natural living world. Okay, so it has learned itself how to be sustainable. Otherwise, so many millions and even billions of years, you wouldn't see the living forms being around. So there is so much to learn from, and we shouldn't be shy about mimicking, actually. Mimicking is a very loose word. Mimicking a living being is such a tough game, actually. But nonetheless, whatever we learn, at least at the preliminary level, we should be able to take them into our research and take forward our research in the same way. So, in a way, lessons we learn from nature can be translated into our research activities. So, the core topic I have taken is to speak about artificial intelligence. You may say related to material science, sustainability, what artificial intelligence has got to do with it, right? So I just want to take you through and tell you that the way we means my generation, developed, that technology is not viable. You as younger generation have to find a new technology that is as good as what biology has done. How it has created intelligence can we somewhat mimic or do things the way nature has done. This is actually the summary line, the conclusion line. In a way, I'm actually done with my talk. But I'll show you some of the attempts we have made in the laboratory, okay, for the next half an hour or so. Let us begin with sort of an overview where we stand with respect to artificial intelligence. So here we expect a machine which is intelligent in an artificial way to learn from experience and adjust to new inputs and perform human-like tasks. These are of importance in healthcare, autonomous vehicles. Even in India also, I think some companies have come forward now launching of driverless cars and all, and big data handling, and also data security. So all these areas we need very good applications of the artificial intelligence. And what is a very humbling experience for mankind is that over the years, through semiconductor revolution, through VLSI, whatnot, we learned how to make storage of information in very narrow spaces. It has now gone down to around below 10 nanometers or so. And also learned to develop very so-called fast processors, put them in parallel and make them so-called supercomputers, whatnot. And this is a very old example. Why I'm showing this is from the 90s. Why I'm showing this is, we still are there where we were. I mean, I'll also put out some plots and all. So you can look at such a huge computer, what energy is required to run it. You know, if you look at a rodent, a mouse, if it has to do some action, or we ourselves, what kind of energy is required? It's only about few watts of power. Whereas for such a powerful supercomputer to do a similar task, not only it will take longer time, it will also be consuming a lot of energy. I have the first-hand experience as an administrator in my research institution. We have the National Supercomputing Mission related a node in our campus, and we had to set up. And we had to draw a very thick electrical cable and dedicate some space for chilling plant and uninterrupted power supply, another uninterrupted power supply just in case this fails, and then run all the nodes. I mean, this is humongous actually. This is not the way biology works. You and me exist because we take little food in the morning and we are already up and we are, doing many things, multiple tasks. So somewhere on the way things have gone wrong and it is hitting us very hard. What is our carbon footprint today? I'm not talking about the overall carbon footprint, that is yet another figure. I'm just talking about the digital footprint, and it is estimated that, I'm just doing some comparison, 4% of global greenhouse gas emissions, and that figure is comparable to aviation industry. Let's not get into the real figures here. See, you see so many aeroplanes taking off, landing, right, all over the airports globally. So if you look at, this figure what we use in data transaction, making our computers work, making our cell phones work, and that apparently is very comparable. I didn't realize that. I mean, there are some sources, some calculations exist on the internet you can look at. So day in, day out, the first thing anyone does this morning was to just get up and look at the cell phone, notifications, blah, blah, turn off the alarm clock and emails and whatnot, or coffee, get started, and already you would have finished a dozen calls, right? And replied to several emails, and you will be on other tasks. So look at it, 8 billion people, maybe 5 billion, 4 billion will have such access to such computers, such gadgets, and look at the energy consumed there. You may say, my thing lasts for 12 hours battery, but somebody has to supply power to the battery, so it goes on. If you look at the route where the energy is coming up, it all adds up, and that can become comparable to aviation industry, what this particular reference is saying, and it is believable actually, if not somewhat there. It's a huge amount of energy which is required. When we talk about AI, there are many avatars to that, okay? Many terms we talk about, artificial neural networks, machine learning, deep learning, and neuromorphic devices, neuromorphic computing, whatnot. But, in one way or the other, I'm going to stitch all of them together. You have been using ChatGPT, right? Tell me one of you who has not seen, heard, or not used ChatGPT at all in the hall. I'll announce a prize for that individual. None, you see. So today you have again many versions of ChatGPT, right? And every day it's evolving. In fact, I became a subscribed user of Perplexity AI. I'm not doing any marketing for them. I'm just studying how is this. I want to jump to another one. Now my colleague told me another one is some other product is much more smarter. So I think next month I'll subscribe to that and try it out. Why not? I'm just trying out. But I keep telling my students, this is a very important message. You can use calculator to computer to AI, anything you want. But finally what you put down, proof of the theorem or whatever writing you do, you are responsible for it. You should be understanding what it is and you are responsible for it. So there is some take-home message for students. So while doing so, I also spoke about the energy aspect. You can now see if all of this is working under the cover of artificial intelligence, doing particularly data processing and data storage and transfer, it's energy consuming, and that is not sustainable at all. And where we are going wrong, something is wrong, right? Do you sense that? You can see here, this is a plot. I'll just try to take the cursor out, if I can. Oh, there is some issue there. Oh, yeah. No, it doesn't matter. Do you see the arrow there at the bottom? A star figure there? That is the brain. I am plotting here power density versus the clock frequency. Brain is rather slow in doing tasks, but its energy consumption, power consumption is also extremely low. But it does in a very peculiar way. When we say its processing speed is low compared to other super duper computers, it doesn't mean that it doesn't do a good job. It just does optimally what is required to be done and not extra, no less, no more actually. But if you look at all the so-called advanced computers, they stand up the curve. This is from the references are given there. You can see their power requirement goes up. This is a log scale actually, right? You can see that it goes up exponentially. Something is wrong. I'm trying to send the signal. Something is really wrong. What is that? Just look at it. Human brain, it consists of 10 to the power 11 neurons massively interconnected to 10 to the power 15 synaptic junctions. There are neurons, which are the processing units. There are also memory unit. Do you have here somewhere CPU is there, somewhere some RAM is there, somewhere? No, it's all combined. Somehow the brain does that, right? So you have so many neurons. Each neuron is connected to another 100 to 1,000 neurons, so on and so forth. That's the bio-neural network. And on the whole, it consumes 20 watt of power. Biologists say human brain consumes a lot actually compared to animal brain. That is very true. Proportional to the body, our brain takes 1/5 of the power. Be it so, compared with computer, they are taking orders of magnitude higher power. Okay? So, as I said, something is seriously wrong. What it is, we need to analyze. If you look at computers, they come in one Neumann architecture, no exception at all. So whatever gadget you are using today, laptop, phone, anything, underlying is what is called one Neumann architecture. It's very interesting how we got into this and all. I don't have time to get into that, but one Neumann architecture, you have the processing unit and the memory unit which are separate, and there's a bus bar which connects them. So it's like a Jaipur main road. So you have traffic going on, the data traffic going on, and that bandwidth also decides how efficiently you are able to do. And such a structure is not there in the brain. It's altogether different. And also computer deals with zeros and ones, right? And whereas human brain is all entirely analog computer. Levels will define. And that is done through spiking and all that. So there are no zeros and ones here, no separate processing and memory unit here, but it does a wonderful job, which is highly sustainable. But all other computers, artificial, whatever you are using, they're all made up of zeros and ones, okay? Well, these are tutorials for neural network. Whatever we are doing, so-called, the sad part I'm trying to tell you, you may have artificial intelligence working with you on your cell phone, okay? Underlying the architecture is one Neumann, where memory and processing units are held separate. It is costly, energy costly. And also it is dealing with zeros and ones. Again, it's not an efficient way of doing it. On top of that, ironically, people have learned how neurons work and adopted that on top of this through little hardware, and much of it is software. And that is the neural network, what we are using today. This neural buzzword has become so widespread, biologists have to identify these real neurons as bioneurons. If I just say neuron in Google today, everything comes about computer-related neural network. Doesn't matter. So what we learn from biology, that was translated to what is called this perceptron, the way the neural thing processes. And so, simply put, a neuron receives a lot of inputs, and it integrates depending on some weights and bias, and then the output is thrown away. Okay? So, to say it is very simple, but biology can get very, very complicated. So we have done with the neural networks also input layer, hidden layers, and then the output layer. So each hidden layer now controls different aspects, the edges. If you're talking of a visual representation, it would decide on thank you. various attributes of whatever we are trying to do and go on refining on that, and then finally it makes a judgment of the output. It is somewhat poorly mimicking what probably goes on in the brain. Why I am saying poorly? Because we have poorly understood what goes on in the brain to begin with. So whatever has been understood has been translated to this. It has gone to a level now, in fact, last year physics prize was given to all the discoveries. Very profound discoveries, of course, but what I'm saying is compared to nature, we are still very, very far away, particularly in the context of sustainability. There in the neural network, when we are trying to do, even in the artificial way, there's also something which is a botheration. That is this, which is going out as an output has to come back and do a feedback loop and go up and all that. Engineers who are working in the field would understand, people who write codes will understand, and that's called back propagation. So when you are doing this back propagation, keeping a linear variation with respect to the input is extremely important. If it gets non-linear, then your computational time, the cost will go up. So these things are also finer details one would be required to pay attention to, and whatever I'm going to talk to you and present will have some implication on the back propagation aspect. There is another very important aspect where we are deviating from the bioneural system. You see, as I said, memory and processing are done by neurons, and it is very difficult to take a neuron and separate out where is the CPU part and where is the RAM part and all that. There is nothing like hard disk at all. So this is being done within a given neuron, and actually trying to understand this particular aspect gave birth to the idea of a perceptron, which I showed in the previous slide. Another aspect we need to remember is there is nothing like a permanent memory registry. This is a very serious aspect. You know, I don't know whether you have seen or heard or seen on the YouTube what a data center means. Okay, so you have global data centers mirroring information with one another. So when I search something here, irrespective of where I am on the globe, it connects me and gives me the access to the data. Data centers are working there. You know, they consume a lot of power, they produce a lot of heat. There's also a proposal actually put them near the polar region, so naturally it is cold and you can use it. I don't know whether it's a good idea or not, but companies are progressing towards that. So compared to that, if you take an animal, there's nothing like a permanent memory registry. Okay, so it just stores what is required and then gets rid of as and when something is not really truly required for living. And there are short and long-term, medium-term memories. Depending on that, the hardware keeps changing. This is very, very important. Depending on whether memory is required or not, the connectivity among the neurons goes on changing, and this part has been very well understood under the bracket of Hebbian rules and all. So there's always memory optimization, pruning and rewiring going on in the brain, and we don't have our computers doing that. Once built, that is it. You use it and throw it. Even recyclability of many components is under question. So again, these are all the burning issues in sustainability. So if you take a typical biological neuron, we define a synapse, the middle figure, where you can see the intensity of the signal which is coming in, right? Through dendrites, it collects a lot of pulses. When it crosses a threshold, it fires. This was understood in 1950s, 60s, and it took time to actually convert that itself into the existing computers. And once a synapse is defined, you can actually look at the synaptic current, the current response or the conductance development with time and classify them as short-term memory or long-term memory, depending on how long is the sustenance of conductance. In a way, in simple electronics language, you have a soft dielectric. You have a dielectric can cause a soft breakdown by putting some voltage pulses, so to say. And when the breakdown takes place, it is only for a finite time. And that decides how much is the synaptic weight. Okay? It sounds so remote and unconnected with whatever we are talking, but that is what the intelligence, it carries intelligence actually. So you monitor that with the time, one can define short-term and long-term memory. And this is how neurons communicate with each other through the intensity or the strength of the synaptic weight. And coming to lab, what one can do is, just send out a pulse, for example, a voltage pulse shown at the bottom, and see the response of the device. You build a device using some dielectric, I'll get into the details in a while, and when you're shooting out one pulse, to begin with, it is non-conducting. The medium is non-conducting, it is a dielectric. You shoot out one pulse, it actually generates some level of current. It's not a capacitor, it's actually slight breakdown of the dielectric, and it generates some current through, and so it achieves some conductance. And that conductance doesn't last long, it dies out. Okay? And this is mimicking what happens in the synaptic junction. Here we are trying to mimic and call it as short-term memory. And if you do pulses repeatedly, what happens? You continue to have when we are doing this, there are no zeros and ones, there is no CPU, there is no RAM, nothing. It's just coming back naked, close to what biology does. Okay? Just looking at how neurons interact with each other. Okay? And by doing so, you can already realize many things, okay, including emulating animal behavior. If you do so, you can expect now the device to behave, carry some elementary features of animal behavior. And that is very exciting to see actually. So what we have done is to use these devices to emulate many, many animal behaviors. There is a basic concept around this, by the way. You know, what I just showed you, the behavior of an electronic device, is not a capacitor, it's not a resistor, right? These are shown here in the diagram. On the top left, you have a resistor, and then the capacitor, then inductor, and then memristor. Memristor is a recent thing. In 1971, Professor Chua from Electrical Engineering, Purdue, proposed, going by the symmetry arguments, there ought to be a fourth element, and that was called memristor, because memristor is a resistor whose resistance is infinite to begin with, and it will only gain finite resistance, means finite conductance, depending on how much charge has flown through. Once a charge has flown through, it remembers how much charge has flown through. Accordingly, it will raise its conductance. So, if you measure the conductance, you know how much charge has gone through. You know the history of the electronic state of it. Okay? So, that is the memristor. And that was realized in 2008 in a seminal work which was published in Nature. Since then, worldwide, lots of activities there. When this particular paper came out in 2008, people predicted maybe in a decade time, all computers will be replaced with memristive type of circuits. And will, on the sustainability, I think we'll go more closer to what nature does. Unfortunately, that has not been true. A lot of technological challenges, including the resistance from the foundries which are already established. There is a business model to this. Okay? So all these are important when, in fact, if you're practicing something, keeping sustainability in mind, you also have to be fighting with the established system. Okay? So you cannot be shying away from it. Okay, so synaptic junction is mimicked in the electronic world using a memristor, a memristive component, which job is very simple. To begin with, it is a dielectric, no conductance at all, and you push some electrical stimulus through that, it develops a conductance. Okay, much similar to what a synaptic junction does. Whether the conductance stays forever, then it's called non-volatile, or it stays for a while and drops down, then it's called volatile. Our memories are volatile. Okay, non-volatile is required for some other reason, we'll not get into that. We work in the volatile fashion. And across the globe, whatever people do, most of it is volatility is uncontrolled, whatever neurons they build in. And there are very few groups, including ours, where we can have predictable volatility of the conductance. This is where we enter, okay, along with few more groups in the world. Well, in the last few years, we have tried to do things wherein we can emulate animal behavior, starting from Pavlov's dog model. You may have heard of it. There are a lot of YouTube episodes on these things. Ebbinghaus model, tip of the tongue experience, so on and so forth. But you can go to my website and find out the publications, but I'll not get into that. I just want to show you how you can begin to replace zeros and one kind of a paradigm. Okay, that's what I'm going to get into. So, as I said, there are global effort in creating memory stew devices with volatile memory, which comes pretty close to what a synaptic junction does. And again, in the interest of time, in a regular, technical full-scale seminar, I would be talking about it, but I'll skip it. There are groups, I want to acknowledge there are a few groups in the world who are very serious about it, that you produce a conductance state in the memory stew device, but have it volatile and at your control. Okay, so this is the ongoing activity, very aggressive activity across the globe. I'll come to just our own research. How much time I'm left with? Maybe another 15 minutes I can take? Yeah, I guess so. I started 10, 15, 10, 20. So is that okay, Saab? Please guide me through. Yeah. Because, being a professor, you don't realize till 1 hour goes by and then students start yawning. You're okay? Next 15 minutes. Okay, somebody said like this. That's a good news. Okay, so what is our approach? Our approach is very, very simple. I want to avoid all the fab lab and all that, okay? Very fancy, sophisticated fab lab, I want to avoid. I also want to avoid a CMOS architecture. If somebody has built up over the decades, VLSI, CMOS, why I should hang on to it? Because the foundry is existing. I just want to create my own kitchen in the first place, and in my own kitchen I want to cook something. I want to show to the world that it can behave as good, okay? So you take it or not. So what we have done is here. We just take a glass slide. This afternoon I can do it in your lab here for demonstration if you want. Piece of glass, and on that you can coat just about 30 nanometer silver film and put it on a hot plate at optimized temperature and for optimized time. It will de-wet. When it de-wets, it forms network of structures. And with that you also have an electrode. Typically we can do 2 probe or 3 probe electrodes, but 2 probe is simpler as shown there. These are interdigitated fingers, and in between the fingers is caught up this particular de-wetted silver film. And it somewhat looks like, poorly mimicking the structure of neural network, I would say. Well, to activate, as born it is not good, as born even the biological neural network is very sluggish and dumb actually. So you have to train it. Our babies go through training for years, okay? Our babies are not smart to begin with. They get to be smarter more than what animals can do later. It comes with the hardware, but not at all sophisticated to begin with. So similarly, our device, what we do is we take it through an IV cycle to activate it. So basically increase the voltage. When you have the dielectric breakdown, you see a dielectric breakdown, or you just come back. Okay, so take it through many cycles like this, then the device understands under what condition you want to work. While doing so, you also set up one current compliance. You don't want current to shoot up in the circuit. So it's few guiding factors, and running through several of these IV sweeps, maybe few hundred of them. We normally keep it for overnight activation. So morning it is ready. So you can see a set of experimental IVs on the other corner there, right? And then what kind of voltage, these are all technical parameters now you have to be monitoring to arrive at proper device performance later, device to device variability, and switching also several times you have to do a 2 lakh time, we tried out how the switching is perfect, like the high resistance state and the low resistance state, okay? So it looks like 0 and 1, but we will not make use of that, it is only for checking. So it just has to go do all these routine things to make sure that the device is doing well. Closer look, this is how the device looked like as born, de-wetted film. Does it look like neurons by any means? Somewhat, at least to a physicist. Okay, and then interestingly, very, very interestingly and unknown in the literature, is you take it through extensive electrical pulsing, it forms a set of nanoparticles in between, the same structure. So it is actually putting out nanoparticles from these features, and they get filled up like this. You can see the tiny, tiny white dots. They are our neurotransmitters, okay? Again, a physicist version of the biology. These guys actually end up forming a lot of millions of percolative networks, the filaments. As we apply further, after the training, we want to utilize that. These are the fellows who will undergo surface diffusion and come under electrical action and get connected, so on and so forth. And seeing them itself was very exciting, but today we do it routinely in the lab. We also done some modeling of it, how the percolative threshold can be reached, because we need to reach from one end of the dielectric boundary to the other. So the medium is having lots of tiny gaps. You may have a little bit of tunneling current, but that's not useful for our action. We really want to have connected and then move the ohmic current through it. And to do that, what critical field conditions we need to achieve and what kind of nanoparticle density we need to achieve, all that we have optimized through the simulations also. We got lots of inputs. Okay, now the device is ready. You understood just a pair of electrodes on a glass surface, and in between you have silver islands and lots of nanoparticles to begin with. It is still non-conducting because nothing is connected to anything. They're still isolated. Tiny, tiny gaps. You may see some current coming up of the order of 1 nanoamp, 2 nanoamp when you apply 1 volt across. So very, very little tunnel current may be there. Now what we do through this, we pulse. I've just shown one type of, one example of pulse train. And this is very simple to understand. You do it routinely in the lab. So here the train shown contains 2 volt pulses, 50 millisecond width, 50 millisecond gap. It just goes one set of pulses. What happens now? This much electrical impulse, what are shown are I think just about 20, 30 pulses. You can send out on 100 or something. So when you do that, suddenly a conductance arises, right? How do you monitor that? Yeah, you can put a little reading voltage. Don't put huge voltage, just about few microvolt or something. Then you will see some current coming up and you measure the conductance there, right? And now look at how this behaves. So having sent these many 20 pulses and monitoring with 100 microvolt, I don't expect 100 microvolt to produce too much heating, okay? Not to do anything, just as reading voltage. Supervisory voltage it is called. What happens is conductance develops, you can see here, from nothing to around 2.5 millisiemens. It is actually expressed in quantum conductance, doesn't matter. And it goes on like this. It slightly drops, but finally it drops sharply to come back to high resistance state, 0, right? So it exhibited a level of conductance there. So my synaptic junction, the way I did it in the lab, could exhibit a development of the conductance against electrical pulses, much the same way in the neurons you have action potentials coming, and they attribute synaptic weight, synaptic conductance which comes up, absolutely the same way. So we can do it in the lab, and we can quantify the amount of conductance which is developed, effective conductance, and how long it retained. We call it as retention time. Equations are shown there, very simple way to calculate. And now we have 2 outputs, the conductance and how long its life, the retention. So given these 2, now we can play around. We can microscopically look at what happens in between the neurons, all that. I don't think I have time to get into those strong and weak filaments, percolative networks, how they come and thrive. And they also compete with each other, how the percolative network actually change from one channel to another channel, so on and so forth. They all ultimately give rise to this collective property, which is the device conductance and its retention. Okay, that is what is, as an end user, that's what is important to us. And why at all retention should be there in this kind of device? Why not, once the conductance comes, why can't it stay forever? Because you see, we produce these filaments under highly non-equilibrium conditions through the voltage pulses, right? And when they get connected, they do it under the influence of the electric field. These are all field-assisted movements. Once the field is gone, they start relaxing back. Once they start relaxing back, there will be shrinkage of volume of the filament eventually to get cut. Okay? So we have quantitative models to prove all this, but this is what the summary line is. So that gives rise to finite conductance retention in the device. Yeah, so these are some microscopy pictures, and bottom you can see how a particular filament which would come up and eventually to decay at the end of retention, working at the ambient temperature, because the ambient temperature also gives some thermal energy, and with this actually retention becomes finite. Now, we are now going to play, okay? Moving on further with this, another 5-7 minutes. So, what we do, instead of giving 20 pulses, we begin with some number like 10 and look at the black curve. And then increase the number of pulses, 20. You can see, when I say increase, you come back to high resistance state, and in one go you give 20 to keep the slate clean, okay? 20, and then you come back to HRS, again give 30 pulses, conductance has gone up. You can see now, as I give more, add more pulses in the wave train, more conductance develops in the device, and it also stays longer. Absolutely mimicking what goes on in the biosynaptic junction. We got a handle on that, right? You can plot now conductance versus the action potential numbers. They go linear actually. You see the black curve, that is the conductance, and the retention is the red curve, which is the retention time in seconds. So we can use it in many mathematical operations. Linearity, I just spoke about linearity, right? It's a big deal in the literature because of the context I said, the backpropagation problem. So a lot of review articles have been written on this about the importance of achieving linearity in the developed conductance in memory-resistive devices, and rush of papers you can see here. Lot of papers even mentioning linear conductance update, linearly it's varying, so on and so forth. Yeah, so that's the madness in the literature, just to achieve the perfect what is required to build a good memory-resistive circuit. Well, these have been the challenges. Why, after 2008, still you don't find memory-resistive based computing systems, okay? So people have to address these issues before it can be taken forward. Where we stand. Here we have plotted, potentiation and depression. Going up in conductance is called potentiation, and coming down in potentiation is called depression, because these are biological terms. And you look at the scatter of points from the literature, and where we stand is here. For example, one curve I have shown of our potentiation depression. Conductance is on top, and for the first time we showed even in retention you can have a similar linearity coming up. They are the non-linearity factors, and you can see this in the scatter plot where we stand. There is some noteworthiness of our result from the lab, but world is so competitive, right? I mean, so by the time we came out with publication, there is somebody else putting out even better, so on and so forth. That's how the literature works. We could be thinking of building up artificial neuron networks with this, go one step back and just show to the world, okay, this also works the way you wanted, but that's not our aim. But we could be showing that using ANN softwares, our devices do as good, coming ideal, close to the ideal device. Okay, a few publications are particularly meant for this activity. Now, how we exploit it? I told you that I'm going to show you something working mathematically without using zeros and ones. I just want to demonstrate that and close my presentation. First, as a number counter. So, having kept my device ready, I tell students, tell a number. So, the student tells some 26. Okay, I just punch in 26. It should produce a conductance and retention exactly going with the straight line what I have drawn from the calibration, right? So, first thing is it works like a number counter. Good news, but that's not enough. And then we can actually define mathematical operation. Input one single pulse, you can count it as number 1. 2 of them with a little time space, number 2. And pulses of opposite polarity should be 0, plus 1, minus 1, right? So this is mathematics, nothing to do with computer related. This is just pure mathematics. So I can define my input pulses with these polarities and all. This is, definition. And having done that, I take it to the device. What I do, the familiar, I give 30 pulses, positive pulses, and you see on the other side, emergence of conductance, and it stays for quite some time, few hundred seconds, and then it drops down, okay? That is what is expected of. This is volatile memory, right? Good. Now we give 50 pulses. We have seen it before, that the conductance is higher, then again it drops down. Fantastic. What we do now is, we give 50 pulses, but we will mix the polarities. So what we do, 40 positive and 10 negative. What should be the answer? Human mind. 40 positive pulses, 10 negative pulses. What should be the answer? 30, right? So 30 should be the answer. And what my device gives, let's see. Look at that red line, right? So it did a mathematical operation depending on the pulse polarity, much the same way synaptic junctions do. if you give inhibitory signal, it kills the synaptic weight, much the same way. And you do more mixing now, positive, negative, positive, negative. You confuse the device, okay? And the answer is the same, but then you see the green curve just overlapping with it. It doesn't matter how the pulses came, it is the mixation which matters. And now we thoroughly mix the pulses, okay? Positive, negative, positive, negative. What happens? You see, still it is sticking to the answer 30, right? It is overlapping with that curve. But some very major difference is there in the way it presented the data. Okay, when I send out a neat 30 positive pulses, my signal is very smooth. But when I mix the pulses and send, the output becomes noisy. Look at that, right? Very strange it is. I mean, how a device knew that I mixed the pulses. It knew the strength of the pulse, number of pulse, the polarity of the pulse, and the pattern, the sequence in which the pulses came. Everything matters, right? Is this the way the biology behaves? Yes. Look at that. Presynaptic noise carried forward to postsynaptic events. There is biology equivalent to this. For the first time we realized and put out, and I had a lot of communication from experts worldwide. Oh, wonderful that you have seen it, what bioneural networks actually exhibit. So we have today in materia calculator, that is not your ordinary calculator. Ordinary calculator, what you have, it's all based on zeros and ones and von Neumann and all that. But this one is not. In the material itself, it is cooking up the computation. It is doing there is no zeros and ones here. I think this should be the way forward to realize how to come closer to the way the biology works. Well, many examples, the accuracy levels we have monitored, and then I should be just closing now actually. So lots of such examples. Anybody interested later on during tea break or lunch break and all, I can sit with you and explain out things. We actually came up with how much error it is doing. If you mix a lot before you feed into the device, mix the polarities, it does calculation well, but the standard deviation around it is more. So it is able to sense the mixing as well so well. Okay, the conclusion is you don't need a big fab lab, particularly in India. I'm not talking about advanced countries. Particularly in India, we suffer not having good fab labs. The closest one you can now reach out to is probably MNIT should have one small scale, but I think IIT Delhi or IIT Bombay and all that. We don't have too many fab labs. Semiconductor, the CSI lab will have one. But still access, day in, day out access and working is so difficult that we have to develop something on our own. Being in Bangalore also I did it because it's my passion. I could have approached some fab labs, but it is my passion to stay with sustainability type of issues. Okay, so I think we can take it to even more complicated to computation, but I just showed you arithmetic way of doing calculation, but I can really make life very complicated, but that's not my aim. I just want to end here. I want to tell you that when we do something in the lab, it's also our passion to take it out to industry. Okay, if I do something in the lab and publish, and maybe I will patent one step further, but how the world will know, right? So what we do is actually produce prototype boxes, and we make devices, and actually Pavlov's dog model, the neuromorphic demonstration of that, we built a box, and whenever these college students and any visitor comes, we make them play around with these boxes and realize the neuromorphic functionality. That is also one of our passions. Where it is heading to? Well, with this kind of non-CMOS geometry of the device, we are not doing crossbar at all. We are just doing in-plane devices. We are heading towards what's the emerging area of reservoir computing, and that too in materia, using material science, how to come up with reservoir computing. So this is our way forward. Already we have some very good results in the lab. I'll share it with you maybe next time. And a couple of students, Bharat, Indrajit, so on, can show, and some collaborators and also funding agencies I have acknowledged here. Thank you very much. Organizers have to tell me whether Q&A you want to take up now or later. Then you have to have some microphone moving around.
If anyone has any question, you can raise your hand. I'll pass on the mic. Yes, sir.
Sir, first I introduce to you. My name is Professor Ramphal Sarma, and my student Abhay Sagade
Oh,
already work out with you. And thank you for giving the new idea to us. And we hope we will continue here this work in Jaipur. And my question is this, how sustainability and stability of the nanoparticle with respect to the industrial touch?
with respect to industrial?
Industrial touch. If we
If they
make
take
the
it to-
industry, then the sustainability and reproducibility will be there. Because we know that in nanoparticles, it is a big problem to solve that problem. So how to solve this problem?
No, you are talking about the results I presented,
Yeah,
right?
yeah, yeah.
This is all just silver.
Silver, yeah.
Silver.
Yeah.
So, silver, we make jewels and vessels and all that, right?
Yeah.
And they stay with us for ever, actually.
Yes, sir.
I still have silver cups what my grandma presented me. So, silver is all around. It is the amount of silver which is used here
Yes.
is absolutely minimal. And the nanoparticles which are produced are of the order of 20, 30 nanometer. Okay?
Which technique?
The most interesting aspect I need to tell you is, having made the nanoparticles, and if you leave the device unused, okay, you are not going to trash it, but unused for a very long time,
Yes, sir.
the moment you again start to use it, it doesn't work with you. It doesn't respond.
Yes.
You need to undergo the training part.
Yes, sir.
Okay, so in a way it is similar to what biology does. But otherwise device doesn't degrade.
Yes, sir.
Once made, it is useful. And if I am telling industry that I am making use of only just silver, nothing else, they would hug me actually.
Yes, sir.
There is nothing else toxic here.
Yeah, okay, sir.
Yeah.
Okay, sir. Thank you very much.
Thank you.
Excuse me, sir. I am Dr. Nishan Gaur from JECRC University. I am asking some simple question which is related to neurons. Neurons play an important role in case of depression. Neurons play an important role in case of depression. What is your views about this statement?
Yeah, this is a very difficult question. So, depression, when I refer to, I am borrowing this term from neuroscience, okay, which deals with one aspect of synaptic junction. The synaptic junction can get potentiated, it can get under depression, means the conductance level drops down. It's only a technical term used. But cognitively speaking, depression it's another world actually. I'm not talking about that. I have no authority to talk about it.
Because you are talking about the neurons, so have I...
No, it should not be misleading. This is just a technical term neuroscientists use for the synaptic junction. Same thing is borrowed in physics also. Yeah. Cognitive, the behavioral aspect, depression and all, it's a different scale altogether. There's no physics for it.
Thank you, sir. Thank you.
Students, please.
Hello. Thank you very much. Okay. Hello, sir. I am Anita Nehra. So your talk is very inspiring. The way you started, from the glass surface, you have developed the silver strips and then nanoparticles. So this basically brings out a very basic thing, like what a researcher should think that we should not, like being in a university setup, we have very much limitations. You have already mentioned that we have so much limitations in India, as well as if you go from JNC, ASR like labs to these university labs, we have lot of limitations. Basic to develop a basic research itself. So, what is your suggestions and guidance, and maybe the encouragement to the university setups and the low level setups wherein people can do research as well as they can excel in the basic fundamental science, like you have showed very good example. So thank you so much, first of all.
Yeah, we should look at those countries, how from very difficult times they have progressed. I mean, Japan is an example. South Africa I visited. Many places are thriving now because the kind of effort they put in at the government level, at the society level, education systems. In India it is happening, but it can happen even more. I'll just borrow what I come from. Professor C.N. Rao's family. Okay, he used to always say something. When he joined IIT Kanpur in the 60s, he said, I had to make my own space, I have to make my own water, I have to make my own air. It has, don't translate it literally, what it meant is exactly what you are asking. So it is just individual's passion and drive. You will always find a way out. So being in university can actually is a blessing in disguise actually. If you are in a very some great place, so-called great place, your brain may not get teased a lot. I don't know. So it just depends on individual's effort and passion which drives. Of course, it is good to be close to some established system. I agree, but it cannot be stopping one. Yeah.
Sir, I was curious about this one thing because when we say we have an habit, right? So in neural pattern, there is, we call it myelinated habit. So fat cells form around that neural structure, like habit of studying, running, going to the gym. So we say that we have that connection is very fat, makes the connectivity very fast. So is there a potential for that happening in this as well? Whereas some processes, if repeated once again in a periodic time, might get faster, like just how the brain works. Is there a possibility of that in this?
Yeah, I have, it's a very interesting, difficult topic to discuss, but I'll try to put it in simple terms. See, there are many layers to learning and memory, many layers to it, okay? So, I may have learned some game, badminton or something. Today, if you give me some racket and ball, I know the rules of the game, but I cannot do it immediately, right? The right kind of things have to get triggered, so to say. Same thing happens here. So when we are doing more complex tasks, and some tasks we left behind without doing much, and we want to revisit, the device will do, but it takes time. It goes through a little more circle of training and all, and then. So in fading memory, learning, they're all closely related. And as we speak more, we should be also guarding against slipping into, hypothesizing much more than what it can deliver. Okay, so in a simple way, yes, we are able to realize whatever you are saying. Shall we close here? But students didn't talk anything. Yes, there is one, please. Microphone, please. Okay, otherwise, please shout.
Sir, you showed the graph, and I think that graph, I understand a little bit of it. So my question to you is that how did you came up to a simple idea to show that this simple kind of setup can represent the biological brain?
Okay, so what on earth made you just, you dreamt about it, you got up in the morning and started working?
What was the spark?
No, I know, I understand. No, there is background to this. I showed the last slide. What is comes under reservoir computing. In reservoir computing, one deals with a system, putting it in physics terms. It is not too disordered, not too chaotic, but it can take some low dimensional inputs and convert them into higher dimensional output. Okay, these are typically nanowire networks, particulate networks, but what we wanted to achieve was hierarchical systems wherein there is scope for everyone to exist, a big one, small one, but highly intermixed. So we were hunting for it for nearly 1.5 years. Finally, we landed upon that. The spirit comes from reservoir computing. Good question.
Thanks.
There's one question at the back. The organizers have to tell, we are ready to stop anytime you indicate.
Sir.
Hello. Good morning, sir. My name is Ayush Saxena from BTech. So, you explained ABI, Artificial Biological Intelligence. I have a question that how can it inspire AI? Can it inspire AI or can they work together?
Okay, so can this eventually become what present day AI is doing? Okay, answer is I do not know. And whatever we are doing in so-called biologically mimicking and doing, whether it can also interface with the present day tech AI, yes. And so in fact, people are working, there are groups working on taking reservoir systems, working with the present day AI systems. In fact, the readout is made from the regular AI, okay, the CMOS and all and regular AI, but the initial computation, hidden layers are being, see if you have ANN, you will have input layer, output layer and a lot of hidden layers, right? If you can replace one hidden layer, already you are saving a lot of cost. So the hidden layers are being replaced by reservoir computing. That way, the interface is already coming up. But whether it can altogether eliminate, I'm not sure. I don't know.
Thank you, sir.
Thank you.
Okay, as we are running out of time, the students, if you have any more questions, we can take it in the high tea round or during lunch as well. Or even if you have any detailed query, you can even mail it to sir. Okay? Thank you so much.
Thank you.
Thank you so much, sir. Your talk has set the tone for the research for sustaining human life as the aim of the conference, and we are very, very, very thankful to you for that, sir. So as a mark of our gratitude for being with us today, I request Professor Victor Gambhir, sir, to kindly give sir our gratitude token. I request sir once again to be on the stage. So Victor Gambhir sir is requested to please present a certificate and the memento to Girdhar sir. Thank you so much, sir. So this is the right time and the perfect platform to introduce a wonderful segment. भौतिकी यानी विज्ञान की वो शाखा जो हमारे चारों ओर की हर गति, हर ऊर्जा और हर घटना को समझने की कुंजी है। और जब भौतिकी को समझना बोझ नहीं, एक रोमांच बन जाए, तो वही है अन्वेषिका फिजिक्स भारत यात्रा। For this, I would like to invite Professor Y.K. Vijay, Professor G.S. Menaria, Mr. Y.C. Sharma, President Sir, and Pranav Saxena, sir, the convener of the conference, to please be on the stage with the e-mashal. So to give us a brief about the mashal, I request Professor G.S. Manaria, sir, to please address the audience.
Honorable Dais, Chief Guest, Guest of Honor, Director Sir and Registrar Sir. Physics Bharat Yatra, I am representing here Indian Astrophysics teachers to create interest from the childhood. Initiative is taken by IAPT. IAPT has set up 35 centers in India called Anveshika under the leadership of Padma Shri Professor S.C. Verma. He is from IIT Kanpur, retired professor, an eminent physicist of the country. Everyone is proud of him. During Anveshika, we create the workshops in non-conventional way. Just we were talking about the problems right from the childhood and the research. So we set up 35 centers in India to create interest right from the beginning in non-conventional way, like potentiometer, ammeter, or all the things. We are creating the interest at the basic level. An exam called National Anveshika Experimental Skill Test is also set among the Indians. And just to come out, this, just to tell about this Anveshika Physics Bharat Yatra or E-Mashal, to create interest, this Mashal Yatra was started from Jammu Kashmir on 5th of May in presence of Governor Lieutenant Manoj Sinha ji, President IAPT and Professor S.C. Verma sir. From Jammu Kashmir, it is entered to Himachal Pradesh, IIT Mandi, then Uttarakhand, entering into Delhi, Punjab, Chandigarh, and finally it entered into Rajasthan at Bikaner. From Bikaner, it is brought, this Mashal Yatra is brought to Jaipur, and till now we have covered 20 major institutions, colleges and universities here to conduct the workshop in very innovative way. This Mashal Yatra will wind up in May at IIT Kanpur again, where all the 35 center coordinators will get together to share the experience and how to make the subject very innovative, very interesting from the childhood. This is an input in the form of this e-mashal. We are thankful to the management that this mashal is today brought to the dais of the JECRC University. And secondly, I wish to invite the management of JECRC University and the dignitaries that a unique concept in India, rather I can say in word we have started here in Jaipur, in the name of Physics Dham, where 300 concepts of physics are displayed in a very unique way. The equipments of 20 countries are brought under one roof, and which explain physics in very interesting way. Even a 6th class, 5th class, 3rd class student can understand higher physics easily in the tourism. It's a place of tourism, only 2 hour journey. I invite the management and the students who are having a difficulty in physics can visit the place and create a lot of interest. It's not a measure. Now we are not lagging under the leadership of Prime Minister Narendra Modi ji. Now nothing is impossible in India, just to set that pattern, the values, and just to come out that country. Now the research can be started right from the beginning. In Jaipur, we have started that concept. It's a very unique
speaker and connect it with 50 hertz means adjust the loop. You can teach the concept of quantization, which is the need of the day. You know, the quantum science we are talking about, 2 pi r equal to n lambda, that can be taught in a very simple way. So there are many such innovative models designed and developed, which can be bought at any institution. That is the mission of IIPT, and being a responsible for the state, when any event which takes place in Rajasthan or even outside, we support. This time we are supporting the good research paper on innovation as a cash prize of 3,000 rupees and 2,000 rupees second prize. For posters also, we will support that to encourage the young researchers to come forward. Much for giving this opportunity, and it's a wonderful platform, and I just jumped upon this opportunity to meet the giants of physics nationally, internationally, and of course locally. So we talk about the local, and still we wish for a global perspective. Thank you. Regards to these dais.
Thank you so much, sir. That is an amazing initiative which has been started. So as we come close to the end of this glorious day, I request Shivani Agarwal ma'am,
Punjab, Sindh, Gujarat, Maratha, Dravida, Uchchala, Jaladhi, Taranga. Tava Shubha Name Jage, Tava Shubha Ashish Mage, Gahe Tava Jaya Gatha, Jana Gana Mangala Dayak Jaya He Bharat Bhagya Vidhata, Jaya He, Jaya He, Jaya He, Jaya 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 He.
thank you so much. We will now be collecting for the group photographs, and after that we will be going dispersing for the high tea. But I request everyone that we have to collect back in KAB 6th floor seminar hall for the session after your high tea. Until then, please remain seated for the group photographs.